In the vacuum of space, 380,400 kilometers from Earth, lies humanity's next great frontier. But the moon is not a gentle host. For 14 days, it bakes in solar radiation. For 14 more, it plunges into a darkness colder than any place on Earth. By 2035, we plan to power our lunar cities with something that has never been attempted at this scale. Nuclear reactors, operating autonomously in one of the most hostile environments known to humanity. This is the story of how we're preparing to split atoms on another world. The lunar surface presents challenges that make terrestrial engineering seem almost quaint. Temperatures swing from 127 degrees Celsius in sunlight to minus 173 in shadow. There is no atmosphere to provide convective cooling, no water for traditional reactor systems, and no margin for error. Solar panels, humanity's go-to power source in space, become nearly useless here. During the moon's 2-week night, they generate nothing. The dust that covers everything is razor-sharp, sticky, and toxic, capable of destroying the most sophisticated equipment. But nuclear reactors offer something different: continuous power, independent of the sun's cycle. High energy density that doesn't require massive battery banks. The ability to operate for decades without human intervention. The first nuclear reactor operated in space in 1965, America's SNAP-10A. The Soviet Union followed with over 40 nuclear-powered satellites. But what we're planning now is fundamentally different in scale and ambition. NASA's Fission surface power project aims to deploy a 40-kilowatt reactor on the moon by the early 2030s. China and Russia plan an automated nuclear installation by 2035. Private companies like Westinghouse and Rolls-Royce are developing microreactors specifically for lunar deployment. The question is no longer whether we can put nuclear reactors on the moon. The question is how quickly we can make them work. Dr. Lee Mason has spent the last decade thinking about reactors that will never be serviced by human hands. As NASA's technology manager for power and energy storage, he oversees the Fission surface power project, America's most ambitious attempt to nuclearize the moon. The reactor they're designing weighs 6 metric tons, generates enough electricity to power 30 households, and must operate flawlessly for 10 years without maintenance. It will be assembled by robots, deployed by rovers, and monitored from Earth across a 250,000-mile communications delay. The moon doesn't forgive engineering mistakes, Mason often tells his team. Every component must be qualified for radiation levels that would kill a human in minutes, temperature swings that would shatter most materials, and a micrometeorite environment that constantly pelts the surface with debris traveling at bullet speeds. The reactor core uses what's called HALEU, high-assay, low-enriched uranium. It's a compromise between the highly enriched uranium that would be most efficient and the proliferation concerns that come with weapons-grade material. The fuel pellets are encased in multiple protective layers designed to contain radiation, even if the reactor suffers a catastrophic failure. But fuel is only part of the challenge. Heat rejection in a vacuum requires massive radiator panels that must be deployed automatically. Power conversion systems must work in an environment where lubricants boil away and metals become brittle. Control systems must be intelligent enough to respond to problems that ground controllers won't know about for 3 seconds, an eternity in nuclear engineering terms. The first phase contracts went to Westinghouse, Rolls-Royce, and General Electric in 2022. Each team was given $5 million and 18 months to prove their concept could work. The winner would build the reactor that powers humanity's first permanent lunar base. But they weren't the only ones racing toward the moon. In Moscow, nuclear engineers were already designing their own lunar reactor. Unlike NASA's methodical safety-first approach, the Russian-Chinese collaboration embraced a more radical vision: full automation from the start. Their reactor would be delivered to the moon, assembled and activated without any human presence whatsoever. Advanced robotic systems would handle everything from site preparation to waste management. The technology demonstration was scheduled for 2033, 2 years before NASA's target. The announcement sent ripples through the international space community. Suddenly, nuclear power on the moon wasn't just an engineering challenge, it was a geopolitical race. Dr. Sarah Mitchell, who leads Westinghouse's Space Nuclear Division, remember the moment the Chinese announcement broke. We realized we weren't just building a reactor, she recalls. We were building the foundation for whoever would control lunar resources for the next century. The implications were staggering. Nuclear power wouldn't just keep the lights on in lunar habitats. It would enable the energy-intensive processes needed to extract water from lunar ice, manufacture rocket fuel from lunar materials, and support the industrial infrastructure needed for deep space exploration. Whoever mastered nuclear power on the moon first would hold a decisive advantage in humanity's expansion into the solar system. But with that opportunity came unprecedented risks. A nuclear accident on Earth can be contained, managed, evacuated from. On the moon, there is nowhere to run. Dr. James Werner studies the intersection of nuclear safety and space exploration at MIT. His calculations paint a sobering picture of what could go wrong. A reactor meltdown on the moon doesn't just affect the immediate area, Werner explains. It could contaminate potential mining sites, scientific equipment, and future landing zones for decades. The lack of atmosphere means radioactive particles could spread across vast distances. But Dr. Rita Baranwal, former U.S. Assistant Secretary for Nuclear Energy, argues that modern reactor designs have evolved beyond the failure modes that caused historical accidents. These aren't the reactors of Chernobyl or even Fukushima, she notes. Triso fuel is literally meltdown-proof. The physics of the reaction means it cannot run away from itself, and passive cooling systems mean that even if everything else fails, the reactor will safely shut itself down. The regulatory framework is evolving as quickly as the technology. The UN's 2009 International Safety Framework requires comprehensive safety assessments for any nuclear mission. The U.S. Interagency Nuclear Safety Review Board now evaluates every launch that carries nuclear materials. But gaps remain. There are no established protocols for nuclear waste management on the moon. No clear jurisdiction over reactor sites that span multiple countries' claimed territories. No precedent for who would be responsible if something goes catastrophically wrong. Environmental groups worry about setting a precedent for nuclear industrialization of space. Indigenous rights advocates question the ethics of claiming celestial bodies for resource extraction. And some scientists argue that the risks outweigh the benefits entirely. Yet the momentum continues to build. The economic logic is compelling. Transporting materials to the moon costs approximately $100,000 per kilogram. A nuclear reactor that can operate for decades represents an enormous cost savings compared to constantly resupplying solar panels and batteries. In March 2018, in the Nevada desert, engineers achieved something that had been theoretical for decades. The Krusty experiment, kilopower reactor using Stirling technology, successfully demonstrated a space-qualified nuclear reactor under simulated lunar conditions. For 28 hours, the small reactor generated electricity, while subjected to temperature extremes, vacuum conditions, and radiation exposure that mimicked the lunar environment. Every system performed exactly as modeled. Every safety protocol worked as designed. It was the proof of concept that the space nuclear community had been waiting for. Dr. David Poston, who led the Krusty team at Los Alamos National Laboratory, watched the test data stream in real time.
This is the Krusty
We knew we had crossed a threshold, he later said. Nuclear power on the moon wasn't science fiction anymore, it was engineering. But Krusty was just 10 kilowatts, enough to power a few houses. The reactors being planned for lunar deployment are 4 times more powerful and must operate 40 times longer without maintenance. The technical challenges remain formidable. Lunar dust will accumulate on radiator surfaces, reducing their efficiency. Micrometeorites will gradually degrade structural components. Control systems must adapt to problems that no Earth-based simulation can perfectly predict. Yet the engineering solutions are converging. Heat pipes eliminate the need for mechanical cooling systems. Triso fuel provides unprecedented safety margins. Modular designs allow for factory assembly and simple robotic deployment. By 2026, X-Energy plans to have a demonstration reactor ready for lunar launch. By 2029, Rolls-Royce aims to deliver its microreactor to the moon. By the early 2030s, NASA expects its first operational nuclear power plant to be generating electricity on the lunar surface. The infrastructure they enable will transform humanity's presence in space from temporary visits to permanent residence. The nuclear reactors being designed today will do more than power lunar bases. They represent the technology foundation for humanity's expansion into the solar system. Mars missions will require nuclear propulsion to reduce travel time from 9 months to 3. Deep space exploration will need power sources that work billions of kilometers from the sun. Asteroid mining operations will demand energy densities that only nuclear reactions can provide. The moon serves as our testing ground, close enough for communication, remote enough for isolation, harsh enough to prove that our systems can work anywhere. But perhaps the most profound impact will be philosophical. For the first time in human history, we will have created a source of energy that operates completely independently of Earth. Nuclear reactors on the moon don't depend on terrestrial supply chains, weather patterns, or geopolitical stability. They represent the first step toward true energy independence for spacefaring civilization. In the coming decade, robots will assemble reactors on the lunar surface. Uranium will split atoms under alien skies, and the power generated will light the first cities humanity builds on another world. The age of nuclear space power is not coming. It has already begun.